My name is Shay Gadot. I'm from Israel. I'm a master's student in the Hebrew University of Jerusalem. And in my master, I participated in a research concerning verifying groups in linear time. So what is exactly the problem? The problem we approach in our research is constructing an algorithm A, which gets a multiplication table T, which is a table where the element in the Tij spot is the multiplication of the Gi element in Gj, and returns an indication whether T corresponds to a group G with some action over it. Okay, so the natural question now is how efficient can A be? So before we approach this question, we need to understand exactly what A needs to verify in order to verify G as a group. So A must verify three things. Number one, the existence of identity element. This can trivially be done by going through all rows of the table and making sure there is one element which all other elements stay the same under the multiplication with it. So this can easily be done in O n squared. The second thing is existence of inverse, making sure in each row of element there is the identity element, meaning there's another element which their multiply equals the identity. Also can be trivially done in O n squared. And the third thing is associativity. Associativity is making sure for every G1, G2, and G3 and G, we can change the order of brackets in the expression, meaning G1 multiplied by G2, G3 equals to G1, G2 multiplied by G3. So the naive way to do that is going through all groups of 3 in G, which trivially costs O n to the third, which is more than we wish it would. So the question is, can we improve it? Can it be done in less than O n to the third? So I'm gonna start by briefly describing two existing solutions. One of them is determinist and the other one allowing randomness. The determinist one is Light's associativity test. Light actually is suggesting to not go through all sets of 3 elements when we check associativity. It actually says that it is enough to go through all sets of 3 elements that where the middle element is an element from a generator group A. So if we have a generators group A, we can only go through all sets of 3 elements where the middle one is from A and the other 2 elements are from G, like before. And this brings us to O n squared log n if we can find such a generated group in the size of log n, which can easily be done efficiently enough. And this is the next claim, that given a group G, a set of generators A such that the size of A is O log n can be found in O n log n. This brings us indeed to time complexity of O n squared log n. The solution allowing some sort of randomness is done in the approach of randomized Monte Carlo. The idea is actually similar to Light's associativity test, only this time instead of finding all generators of G, we can stop at some level according to our error delta. For example, if we want our error to be smaller than delta, we need to be wrong over a set smaller than n delta. So we want our generators, which we go over, to span more than 1 minus delta n of the elements of G. This way we get an error smaller than delta. And the time complexity is actually n squared log 1 divided by delta. So the question is, can we do better? The lower bound to this problem is omega n squared. In our work, we suggest a solution that works in big O n squared. The reason to the lower bound is that the size of the input, the multiplication table, is n squared. So our solution is built of 4 main reductions. Each time we take a problem and we make it easier to solve by reducing it to a more simple problem. So I present this diagram here only for you to understand the flow of our solution, the way it works, and I'm now going to explain each of the parts, and I'm going to come back to it at the end to make sure we understand each one of it. So the first reduction we make is reducing the problem of proving associativity to proving force associativity over a basis of a group. So what is force associativity? Force associativity is a relation of 4 elements in G. We actually want to prove a relation very similar to associativity, only over sets of 4 instead sets of 3. As we see here, the relation is changing all the order of the brackets, just like we do in associativity in sets of 3 elements. And the basis of a group is a set S contained in the group G, where G equals S squared, that is multiplications of all elements in S. Okay, so our claim is that given a basis S of G, G is associative if and only if S is force associative, which we show in our research. And this brings us to solving the problem in time complexity of size of S to the force and our time to find S. Why? Because we only need to find the basis S of G and going over and checking force associativity over it. So what exactly do we need of such a basis S? In order for a problem to be solved in O(n) squared as we want, we need the size of S to be O square root of n, because we take the size of S to the force as we saw in the last part, and we need S to be a basis as we defined it earlier. So we're now going to define a large subgroup. A large subgroup is a subgroup of G that is its size is larger or equal to square root of n, that is the size of G. Okay, we're now going to reduce the problem of finding a basis to finding a large subgroup. So, assuming we have a large subgroup H of G, we can find a basis S of G such that the size of it is O square root of n in time complexity of O n log n. Okay, so the problem is to find S squared equals G, where the size of S is O square root of n. We find it easier to find A and B such that the size of both A and B is O square root of n, and A multiplied by B gives us G, and we define S to be the union of A and B. In our research, in our paper, we describe an algorithm that takes some parameter L that is bigger than 1 and smaller than n, and returns A and B such that the size of A is smaller or equal to L multiplied by 2, the size of B is smaller or equal to L divided by n, and A multiplied by B gives us G. Choosing L to be square root of n gives us exactly the solution we want, because then A is smaller or equal to 2 square root n, and B is smaller or equal to square root of n. Okay, so in this algorithm we make use of the large subgroup. I touched this topic a little bit before we defined it, and the algorithm works in different ways according to the size of H. So the most simple case is when the size of the large subgroup H is smaller or equal to n divided by L, and bigger or equal to n divided by 2L, and then we can choose A and B to be B this H, and then it's smaller or equal to n divided by L, and A and A to be the quotient group G over H, and in that case we get A to be smaller or equal to 2L as we wanted. The other cases of the size of H require further decomposition of H, making the algorithm recursive. And overall, we get running time of O and log n, because each time we run the algorithm is n and we run it up to log n times. And to that we add the time to find H, which is the next thing we're gonna touch now. So the next part of our work is finding the large subgroups for non-simple groups. The first claim is that given a normal subgroup n, we can find a large subgroup H in O n squared, and we're now going to explain how it is done. So if n is bigger or equal to square root of n, then we define H equals to n, and we are done. If it is smaller than square root of n, then necessarily g over n is larger than square root of n. Now, g over n is not a group, but we should use it to try and build one. So how do we do that? We take m to be the large subgroup of g over n, which actually, as we understand, makes the algorithm recursive. And we defined H, the large subgroup, to be m multiplied by n. That we show in our paper that is indeed a subgroup of G, and concerning the size, we get that the size of H is the size of m multiplied by the size of n, giving us size bigger or equal to square root of G divided by n multiplied by n, giving us eventually a size bigger or equal to square root of n, as we initially wanted. Okay, so the running time here is n log n, similar to the last algorithm, plus the time to find n, the normal subgroup. So I'm going to touch now how do we find the normal subgroup n. So we let some normal subgroup n in G, and let the set CGI for I in M to be the set of all conjugacy classes in G. So n must be a union of some of the conjugacy classes. And why is that? Because if we look at the definition of a conjugacy class, this is exactly what defines a normal subgroup, along with the closeness, which making it a subgroup. So a union of conjugacy classes is a normal subgroup of G if and only if it is closed under multiplication. We now define NCGI to be the smallest normal subgroup containing CGI. Why is it not always CGI? Because in the case when it's not closed under multiplication, we need to add elements from other conjugacy classes, and then for it to still be a normal subgroup, we need to add all of the conjugacy class of the elements we add to the group. So we define a graph G to be a graph whose vertices is the conjugacy classes of the group G, and we spin an edge from CGI to CGJ if the smallest normal subgroup containing CGI is contained in the smallest normal subgroup containing CGJ. And then we have no interest in searching the normal subgroup containing CGJ because we'd rather find the smaller one, because we don't want to find a subgroup that is trivial, and we want our algorithm to return a trivial subgroup only if the group is simple. Okay, so after building this graph, we get that every non-trivial connected component of the graph represents a normal subgroup. This means, of course, after we finish spanning all edges of the graph as defined above. So in order to do this efficiently, in each iteration we only go through components that are not reachable. Why? Because since a component is reachable, it means that the smallest normal subgroup containing this component is containing the other one's smallest normal subgroup, and that means that we don't want to invest in this small normal subgroup because there is a smaller one. And if the other one is trivial, this one must be trivial as well. So we don't need to check it, we can only check the other one. At the end, we either find a non-trivial component, nor we conclude the group is simple. Okay, so here we have some illustration of what I've tried to explain in the last level. We start with all vertices relevant, all the green ones, and once we have an edge going from vertex A to vertex B is no longer relevant. That is up until the point where there might be an edge from B back to A, making A and B a connected component, which is up until this level of the graph still connected. So the running time of this algorithm as proved in our research is O n log n. So the last thing we still have to answer is how do we find a large subgroup of simple groups. And that is indeed the next thing I'm going to touch. So let G be a simple group. From the classification of finite simple groups, G is isomorphic to one of the next groups, Zn, An alternating groups, groups of Lie type, or one of the 27 sporadic groups. So the way we approach a group that we understand is simple using the algorithm of finding a normal subgroup. We find a short list of groups that might be isomorphic to G. The initial sort is done by the size. Each family of finite simple groups has a size formula, and we demand it to be in the size of the input group G. This way we can find the parameters defining each of the simple groups. It takes O log to the fourth to find O log n candidates. Next we go through O candidates, each time treating G as the candidate and finding a large subgroup in a way we would find for the candidate. For example, for An we would take An minus 1. It takes O n log n for alternating groups and groups of Lie type, and and actually a constant time for sporadic groups. So to sum it up, we get here the reduction diagram, and we can now build from bottom up the efficiency of our algorithm. So finding large subgroups of all simple groups costs us O tilde of n to the 1 plus epsilon. Finding normal subgroup is O tilde of n. Finding large subgroup of non-simple groups is actually up to both algorithms, so it takes the maximal one, that is O tilde of n to the 1 plus epsilon. Finding a basis would be O tilde n to the 1 plus epsilon. A sensitivity is O n squared, which brings us to a sensitivity in O n squared, which also brings us to determining G as a group in O n squared. So for conclusion, the result of our research is a determinist algorithm that determines whether multiplication table of size n square represent a group in time complexity of big O n squared. That is all we wanted since the beginning. It is important to mention here that throughout the paper we take theoretical results and prove them algorithmically. For example, we know the existence of a basis and a large subgroup in articles made by Lev and Kozma, and we also use the classification of finite simple groups, for example, but we take these results and we bring them into an algorithm. So that would be all, and now I'm gonna get questions.